All right. Now you know how to find a derivative. Let's use that little fella. So the first thing we're going to talk about are maxima and minima. All right. So if I have something, let's just say like this, right? Something like that. If I want to identify max and min, then they have some values, right? So this would be a maximum and this would be a maximum, right? If I have this maximum, this is higher. It's the highest one. So we're going to call that an extreme maximum. This one right here is still a maximum, but it's going to be a local maximum. And it's a local maximum because, yeah, it's still a maximum for that area. It's just not the most that we have. What about this one right here? Yes, we're going to call this one a local minimum because these go on forever and ever and ever. So those are going to be my extreme. But because they go forever and ever, we're not going to have a specific one. All right. So this one only has local minimum in this situation. It has two maxima. One's an extreme because it's the highest possible. So let's put that on here because this one is the highest. Right? And then our local, because it's still a maximum, it's just not the highest one that there is. Okay, so what if we have something like this? Because not everything looks polynomial like that one. What if I have something like this? Let's go down like that. Maybe something like this. All right, a piecewise function. If this is an open circle, you cannot count it. Ooh, right? Because a max and a min is a specific value. It's a specific value that I'm looking at. So in this instance, there is no extreme max that I have. That's an E. There's no extreme max. However, these two values are closed, so we can call those a local max. All right. And this one, even though it doesn't have a specific point associated with it, it's still closed. That one can be our local minimum value. All right. So you're seeing how this goes. It has to be closed, a closed dot, part of my actual graph in order to be an extrema, right? A maximum or a minimum. So it has to have a closed dot in order to be able to pull that off. But you don't have to always have an extreme. Okay? Okay. And yes, I know that it goes right up to this, but when I'm talking about a max, then I want to say, what is that very top? Not how can I infinitely get close? I'm not concerned with that. Just the maximum, full minimum. Okay. All right, so let's look here at example 1. This is find the absolute max and min. Max and min on my closed interval here from A to B. So here's what we have. So here's my closed interval from A to B, and we want to find an absolute maximum and minimum. So we're going to look at part A and part B here in order to come up with this information. All right, so check it out. This is closed because this is a closed dot, right? Here is also a closed dot that I have. So if I just want, I'm going to scoot this in a little bit so we can see it better. So if I just have these, what do you know about the one on the left here, A? Right? A comes up to this one. What do you know about that one? Yeah, it's the highest one possible. So that's going to be my extreme maximum. Another word for extreme maximum is absolute. An absolute max and min. So this one's going to be my absolute max because it is closed. So it is the highest amount. So we're good there. All right. Tell me more things. Do you have an absolute minimum? Yeah, right there at C, right? It's the lowest possible. This doesn't have arrows going off, right? It is closed. It is finite. That is as far as we go. So this is the lowest possible. So this one is my absolute minimum because it's the lowest one possible and it's closed. Okay, what else do we have? So here, that one is a max, but it's just going to be a local max that we have. And this one's going to be a local minimum. And it's considered a local minimum because it's on the down, right? You're going down to get there. All right. Not too bad, right? Okay. Let's do this. What about this next one over here? What kind of information do we have? Yeah, check out all those open circles. With all of that open circle, can I count any of those? No, but I do have one closed up here, and it's the highest one possible, so that's going to be an absolute max. Do I have any minimums to speak of? No, good, because they're all open circle. If it's not a closed circle, then I can't count it. So this one has no minimums to look at. All right, good. Good, all right. So basically, does it hit a peak, right? And is it closed in? Does it count? That's what I'm looking for. All right, let's do this theorem. The local extreme value theorem. The local extreme value theorem. And here it is. If f, so my function f, has a local max or min value at C and f prime of C, derivative, right, exists, then f prime of C equals 0. Check out what this is actually saying. If I have a local maximum or minimum value at C, so some value C, it doesn't matter where it is, and my derivative exists at that value, then the value of my derivative is going to equal 0. This is major. This is telling me that I have a local maximum or minimum. All right, here's our takeaway from this. So what I really get out of this and what I really need to pull from this piece of information here, when your derivative equals 0, that is an indication of a max or min. Now, I don't know if it's an absolute or not. We have to look at that in relationship to the other ones. But I definitely know there is a maximum or a minimum. And if I have a derivative equals to 0, it's not going to tell me which one it is. It's not going to say, oh, I have a maximum. Nope. Oh, I have a minimum. Nope. Because what is a derivative again, right? The slope of the tangent line, right? That's what we talked about this whole entire time. So if I want to talk about a slope of a tangent line, if I have a zero slope, that's what they're telling me. My derivative, my slope of my tangent line equals 0. That's the same thing as a horizontal line. So if I'm touching it at one spot, I get this horizontal tangent. If I'm touching it one spot, I get a horizontal tangent. You get a horizontal tangent whether you have a maximum or a minimum. To determine if it's a maximum or minimum, that is where you look at the points around it. All right? Super cool, right? Yeah. Yeah, it really is. Okay. So, let's go to the next page here. We are going to do critical points. Well, critical values also, but critical points. All right. This is how we're going to be setting ourselves up. Well, how do I figure out a critical point? What am I looking for here, right? So we've done all this factoring and setting ourselves up so it's easier to work with. Critical points come in two situations. If my derivative at C equals 0, that's a critical point. Or if my derivative fails to exist. That is another critical point. They mean two separate things, but I still have critical points. This one up here we learned was a maximum or a minimum, right? If my derivative equals 0, that's a max or min. If my derivative fails to exist, then remember we talked about that continuity. When does a derivative fail to exist? You have those vertical tangents. You've got a cusp. There my derivative fails to exist. I have an asymptote. There my derivative fails to exist, right? So you can have critical points based on these two, but they mean two separate things. Okay, now let's try this one on here. We'll get some algebra under our belt here so that we can find some critical points. So here's example 3. Find critical points. Given f of x is equal to x over x squared plus 1. Now remember, the first way to find a critical point is where I set my derivative equal to 0. So in order to set my derivative equal to 0, I have to have a derivative. We haven't found a derivative yet, so let's find that derivative. So f prime of x is equal to, the derivative of the top is 1 times the bottom. At this point, I just expect you to be able to take derivatives. So if you're still struggling with how to do that, we need to have a different conversation. Because now at this point, my assumption is you're just finding derivatives. So the derivative of the top times the bottom, because it's the quotient rule, minus the top times the derivative of the bottom, all over the denominator squared. Right? So plug this together. I know that this together is going to be that 2x squared. So I've got x squared minus 2x squared is going to be 1 minus an x squared over x squared plus 1 squared, right? I am taking the derivative. Because I have the derivative, you need to write this notation. Use correct notation. That's important. My derivative equals this value. Because my derivative equals that value, then I'm going to set this equal to 0. So let's do it right now. Let's scoot this up a little bit. And we have 1 minus x squared over x squared plus 1 squared equals 0. So what we're actually doing here is we're taking the denominator and multiplying both sides by that denominator. So the top and the bottom cancel. That's just our algebra. 0 times anything is still 0. Every single time. Every single time. So that is going to happen every single time. I'm okay if you skip this step and just go right to here. You're always going to set your denominator, pardon me. You're always going to set your numerator equal to 0 because the denominator always cancels out. All right? Okay, so I'm going to factor this. I've got 1 plus x and 1 minus x equals 0. So x is a negative 1 and x is a positive 1, right? Or you could use the square root property to find this. I don't care how you solve that quadratic. You've got your algebra skills, so do it. But I know I've got these two values. So these two values are critical values, right? This is where I've set my derivative equal to 0. So these are critical values. Now let me squeeze this in. I want to specifically find critical points. So if I'm going to take my points, I have to set this. Let me change my color up here of my, let's go pink on it. I'm going to take these values and plug them back into the original. I want to know what my original equation is, the points on my original function. So you have to plug those in. So I'm looking at f of negative 1, plug that into negative 1 over negative 1 squared plus 1 is negative 1/2. There's one coordinate point, right? So this is a way to write a coordinate point. You could also write negative 1, negative 1/2 as a coordinate point. Same thing. All right, same thing. So f of positive 1, and let's plug that in. So f of positive 1 is going to be 1 over 1 squared plus 1, giving me a 1/2. Let's put it down here. F of 1 is equal to 1/2. Again, there's my coordinate point, or I can write 1, 1/2. Now, just for fun, these are critical points. So this is what I have for my critical points. These are both critical points. My question to you is, by looking at these values, which one is the maximum and which one is a minimum? Yes, look at that. I have a negative 1/2 here. That's small. My y value is smaller, so I know this one has to be a minimum. Here, my y value is bigger at 1/2, so I know that this one is a maximum. Do you see that? Yeah. And is there any possible value where my derivative is going to fail to exist? No. Is there anything I could do to make this denominator 0? No. I'm squaring a term here, and then I'm squaring the whole thing. There's no possible way to take this down to 0. So I'm not going to have anything where my denominator fails to exist. My critical points for this one only are where my derivative is set equal to 0. Not too shabby, right? Yeah, pretty good, pretty good.